Yeah, okay, so we'll start, and we're happy to have Sabin Cautis from UBC, Abelian Hall category. So please, Sabin.
Okay, and so again, please interrupt me if any of the technology goes awry. Okay, so I'll start by discussing the main goal. Um, so the goal of this series of talks is the following: is to be able to associate to a quiver of arbitrary type, not just a finite type or affine type. To associate to it an abelian finite length um, monoidal category. So it's fine. You can read that. It looks okay.
Yeah, it's fine.
Uh,
Perfect.
Um, let's call it HQ, equipped with what I'll try to describe closer to the end of the talk, maybe the third talk, equipped with um, renormalized r-matrices. Okay, and in particular, this put in brackets, this you should think of this category should categorifies. In other words, its growth group recovers the um, the corresponding K-theoretic, which I guess called pre-projective um, Hall algebra, and for let's call it KHQ for K-theoretic algebra. Okay, so that's what I'm going to try to describe. I mean, what is this category? And and maybe talk a little bit about R matrices and some consequences, and maybe if I have time, do a few examples just to illustrate more concretely what the objects are. Okay, so at this point, I could there's another board here. I could move it, right?
Well, whatever is
And give
convenient
you
for
some
you.
time.
The thing is, if you need this blackboard in the future, yeah, you can move it. If you don't need it, you can erase. Yeah,
No, but I want to, yeah.
yeah.
I feel like I can probably write a little bit smaller. No, it's pretty big on the.
Uh,
But it's okay.
well, yeah, that's okay. Then you will have maybe a couple of more lines, but it will not solve the problem permanently.
Okay.
You
I'll try
You
to
can
speak.
get smaller, so if you want to to squeeze more.
Yeah, that's what I'm thinking of writing a little bit smaller. I think I think it's pretty large on the at least on my screen.
yeah.
Okay. Anyway, so that's the goal. So I'll reuse this board for now because I think um and I cannot believe there's no eraser in this. I'm using someone else's uh there you go. I'm in a random classroom and they hit the erasers. Okay, so that's the goal. So it's gonna naturally break up into sort of three steps. One being to define So the corresponding spaces and categories we'll work with. So define, let's say, the moduli stacks. What do I want to call them? XA and the whole product. So that's what we'll do today, hopefully. And then define a T structure on the corresponding categories of coherent sheaves on these spaces.
So when you say coherent sheaves, you mean derived, yeah.
Yeah, I'll be more precise as we go along. So when I write this, I always mean the derived category of coherent sheaves, yes. Yeah. So yeah, I could put a D here, but I'll always mean derived category. And
sorry, bounded or unbounded?
it'll be bounded.
Bounded, okay.
So the typical object here will be some sort of complex, a finite complex of actually coherent sheaves. And maybe and then define r-matrices. All right. And maybe some examples at the end.
So just to, I know that at some point people change capital R to a small r, I believe, thanks to Kashivara. So it will be sort of a meromorphic braiding on that category or what?
Yeah, that's right.
Okay.
So in particular, the data, I'll talk about this probably in the third talk, but the data here is to any two objects, you want to associate a map like this, satisfying a sequence, a family of properties. In particular, this won't be an isomorphism, and it will come from basically a specialization of meromorphic R matrix. But I'll describe exactly what I mean by R matrices. When we get to there, in some sense, that the structure is completely independent of everything else. So we can or cannot. We don't need to talk about that, but I think it's part of it's an interesting aspect, which is worth talking about. Okay. Maybe a remark to make is that if and I'm sure most of you know this, I'm definitely not an expert on Hall algebras. If Q is a finite or affine type, maybe simply laced, then these guys, the K-theoretic or the pre-projective Hall algebras recover the positive half of the corresponding, let me write it out, the positive half of the quantum loop algebra. Of, of G, where this is the corresponding the corresponding Lie algebra. Corresponding to Q.
You know, kind of it's notational remark. I mean, this K-theoretical Hall, I mean, you always mean that it's a pre-projective algebra of Q, because you can also consider K-theoretical Hall algebra of Q itself, and I'm just wondering how would you denote it?
Yeah, it's so when I
if you never use K-theoretical Hall algebra of Q itself, that's okay.
I'll introduce the right notation. For the moment, by this I mean the K-theoretic Hall algebra, pre-projective Hall algebra.
Yeah, okay.
Okay. And the way to remember it is this: there's this category we'll discuss, and this you can think of as the K-theory of it. That's also mnemonic. But I'll introduce the appropriate notation in a moment. So in particular, this category that you get, this abelian category that you get, is finite length, and particularly this it gives you a some sort of canonical basis, a natural basis of this guy. Okay, so that's just some very far. In particular here, just to be clear, if G is a finite type, then you get an affine, a quantum affine algebra in its loop presentation. And if G is of affine type, then you're getting a double quantum affine one. In other words, what's usually called a toroidal algebra.
Probably you are going to talk. So here you are using the coherent derived categories in the constructible sense that this was pretty much known, right?
Right. So this is sort of right. So when you look at let me go to the next to my, I think we'll answer a little bit. Let me get to the next. Let me write something on the board next, and I'll answer your question. But yeah, when you do the pre-projective, so you can consider constructible sheaves on some space, right? Or you can consider coherent sheaves on the cotangent bundle, right? So if you're considering the pre-projective algebra, that's kind of Hall algebra. It's kind of considering if you're considering coherent sheaves on the pre-projective moduli space, that's considering coherent sheaves here, which is supposed to mimic constructible sheaves here. So the fact that, say, if you're taking, let's say Q to be finite, a finite quiver, then if you're doing, say, the usual old, going back to Hall construction of just counting points over finite fields over representation spaces of just Q, that would correspond to constructible sheaves here. And or you can look at coherent sheaves on the cotangent bundle of that, and this is that's being studied here. And when you go from constructible to coherent sheaves, you often, just like when you go from constructible sheaves on moduli spaces, from that to coherent sheaves on Nakajima quiver varieties, for example, you pick up sort of a loop as well.
Yeah.
Okay, so that's where the loop is coming from, the fact that we're working with coherent things. Yeah, so somehow the content here is not to do with this itself and defining these moduli spaces as much as to defining this T structure. Okay. Yeah, so I could have done, for example, I could have done, for example, work out the original example of Hall, going back to view a finite quiver and just counting points over finite fields, and that's a nice example. But given the audience in this talk, I felt like that would be
It's a mixed audience, but at least you can announce. I mean, not to do in detail. I don't know. It's up to you.
yeah. Yeah, so I guess I announced it. If you can well, I haven't even told you what the moduli spaces are. So let me get to it first. So here are the quivers that show up. We have here, which is the original quiver, right? So for example, this might be a finite quiver like this. Okay. Can you see the top of that? I have something blocking it.
No, it's fine.
No, okay. And my screen is just some stupid thing that's showing on top. But if you can see it, great. And then you can associate, obviously, the following. So I've denoted by EL, the following quiver you get by adding a loop at each vertex. Okay, so that's one thing you can do. This is the one we'll use, in fact. So when we're going to consider the moduli spaces of representations, we'll actually consider the moduli spaces a representation of this guy. At the beginning, I said associated to Q, but I didn't mean associated literally by considering the moduli space of representations of this guy. I meant from this guy, you can create this quiver, and from this quiver, you can consider the corresponding moduli space. But just to put things in context, so we can just talk about this one, and that's what the whole talk is going to be about. But I think it's useful to put things in context that there's also the pre-projective quiver, E bar, which corresponds to putting arrows in both directions for the original quiver. So this is the pre-projective one. And lastly, you can combine these two. And what do I want to call it? It's called Q tilde. You can combine these two. Which means you have arrows in both directions plus loops at each vertex. Okay?
So what is something called tripled quiver?
Yeah, exactly, like a triple quiver. So these are the three natural things you can do. Okay. And okay, and we'll focus on this one. So I'm going to try to describe what the moduli spaces we'll consider, and then I'll say a few words how it relates to the corresponding moduli spaces for these others to put things in the context. And this will also go back to a little bit to this question about constructible versus coherent. All right. So the moduli spaces. All right, so we're going to consider moduli spaces of this quiver. So what does that mean? I'm just going to fix notation. Let's say we're going to have the representations. That means that for each vertex, we're going to have a vector space VI.
So A is a dimensional vector, or what?
A is a dimension, exactly, where A is a tuple of dimension vector, is a dimension vector. Okay, I'll just write it A, so it's, I don't know if you want to write an underline under it to emphasize that it's a tuple. And so this is the dimension vector. And we're going to have a series of moduli spaces. So let me write the main one. So the main one is the one I just said, the moduli space representations of this guy. So what does it correspond to? Again, I'm trying to fix notation. I'm going to call it MA. It's a little sort of a double M here, fat M. It's going to correspond to phi x, where phi are the endomorphisms of each vertex. It belongs to that's an endomorphism at each vertex. And the x's are the morphisms between them. So this would be Ham for each edge, Ham from V, the tail of E, to the head of V. Okay? So that's the actual, that's the moduli space.
Stack. I mean, you also have a group. Okay, sorry. Yeah.
One set at a time. So I haven't talked about the group. We're going to portion it at the end, but I need a few tweaks on this space before I do that. I mean, I could talk about that first as well. Doesn't matter. But let me finish about these spaces, and I'll get to the group next. So we have two other spaces inside, which I want to consider instead of this big one. One of them is, I'll denote MA without the fat, which is the one we'll actually work with, is this is just the locus where P is nilpotent. Okay, each of these endomorphisms are nilpotent. So that's obviously a sub space. And inside of here, I'm going to consider this is the I'm going to consider the following thing, and I'm going to write something down and then explain the notation. Okay, MASA, and I'll explain the notation in a second. Let me write it in words what this is. This is the locus where the phis the phis commute with the x's. So I'll write it like this. Okay. So let me explain this notation just because it's also that there's some technicalities involved, just a sort of algebra geometric technicalities. I'd like to.
But just a quick, so the pair actually gives the representation, the boldface M gives the representation of the QL, right?
Yeah, so this is all representations of QL. This
QL.
is a set of them.
Yeah, the nilpotents on each node.
Yeah.
And this one is said that the phi gives actually automorphism.
And this one
automorphism of the representation of Q.
Yeah. Sorry.
Does that commutator relation give that phi is an automorphism of a Q, representation of a Q?
That's right. So you can think of this moduli space as representations of Q plus an endomorphism.
So that's the original Q, right?
That's the original Q, right?
Yeah. Okay, thank you.
So just question to the future. This commutation relation, it's what comes from this cubic potential on a triple quiver when you consider zero locus for the cyclic derivatives.
It'll be related, and I'll explain.
Yeah, okay.
Yeah, I'll explain. So we don't need any of that, but yes, that part of my goal today is to explain that connection. So as pointed out, you can interpret this also as equivalently the moduli space of reps of Q plus endomorphism. Okay. So you can that in. But that's not really necessary or even necessarily particularly
Actually, it's a nilpotent categorifies.
I was, yeah. We can also consider a version of this one, MASA. So put some pen marks in. Okay. But just to be clear about what this notation is, MASA, because there's some technicalities, and since it's a longer series of talk, I'll explain it. Okay, we don't need this. So just as an aside, just the notation I'm using here. So suppose you have a map of vector bundles over some, let's call it S. This is a map of vector bundles. Okay, over some base. Then I'm going to denote by V superscript S. I'm going to denote, which maybe you could argue is not the best notation, but it's convenient. I'm going to denote the kernel, the derived kernel of S. This will be the derived. So everything I'm going to be doing has to be done in a derived setting, derived algebraic geometry. So I'm going to denote this by derived kernel of S. So more specifically, what is it? It's the following fiber diagram. You can write it as V maps to V cross W over X, I guess. And in two ways. One is you can map it as just a zero section. So this is V maps to V0, or you can map it using this as the graph of S. So this would be V goes to V S of V. Okay. And this guy is by definition the fiber product here. It's the kernel, this is the fiber product here, right? But we want to take it in sort of in a derived sense. So if, for example, if V was equal to W, which is often the case in most of our examples, then if S is an isomorphism, so that the kernel is zero, then this would literally be sort of fiber-wise zero, which is the X. But otherwise, this would have a derived component to it. And I'll illustrate this in examples later on. But for the moment, we just use
Pullback, the pullback is in the category of vector bundles.
It's a fiber product of schemes, of derived schemes.
What's the scheme?
Yeah. I mean, I could this more generally, not for vector bundles, but in our case, particularly interested.
One can take a fiber product, the fiber product in different categories. So in the schemes or just the vector bundles. So sometimes the kernel may not necessarily be a vector bundle.
No, it doesn't have to be, but in our case, it will be.
Okay.
Yeah, it's true. This doesn't have to be a vector bundle, but I'm trying to focus on what shows up and is useful for in our case. Okay.
Okay. Yeah. Okay. Thank you.
All right. So given such a map, I'm going to denote V superscript S. Basically it's the derived kernel of this map. So here, this is where this notation comes from. Here, SA is a map from. So let me explain here. So again, this is important, as we'll see later on, for other things as well. So that's why I'm belaboring the point a little bit. But this space here, too many arrows. This space here maps to what I'll denote NA, which is the just the set of endomorphisms phi. Okay, so if you forget the x's, then you just remember the phi's, and this is a vector bundle over NA. Okay, obviously because they're all kind of vector spaces. So this is a vector bundle, and maybe we don't need this other remark here because it's not that important. And this SA is just the map from MA to MA. It's vector bundles over NA given by the commutator relation. By the commutator relation phi x. So this is a map of bundles. It's a map of bundles over NA. Given by this commutator relation, and the kernel is exactly what we're looking for, but we wanted to do it at a derived level, and this is precisely what I mean by that. Okay, so so this explains more precisely what the space is as a derived scheme.
So
yeah.
I think for graduate students, it will be nice if you give an example of quiver with one vertex. So then your Q, whatever, L will be Jordan quiver, and then, yeah.
Let's do, let me finish adding the groups and then we'll do an example.
Yeah, okay.
That way I'm done with the definition at least. So, and then we'll do an example. As I said, I'm going to do, I was going to do examples in later on the third lecture, but it's actually better if you just bring it up and just tell me what to do along as we go, since you have a better feeling what's useful on your end. So yeah, so just to finish the notation of the groups, and then I'll do an example. There's obviously some groups acting on here, and we'll fix the notation just to be precise. So we have GA, again, A is a dimension vector, and this is just a product of the GLAI. So this is just acts on each VI. And then we have a little bit of an extra torus. You can add a much larger torus, but this is sort of the minimal torus, which really makes the story complete. So there's two copies of C star, and they act. So I'll tell you how they act. So T1, T2 acting on phi x is let me write it down and then I'll say a few words. It rescales them in a certain way. Okay, so I'm going to give these names. So this is T1 and T2. It acts in this way. If you look at T1 is the only one acting on the endomorphism guys. So I'll call this one just to have names, but these names have other reasons for calling like this. This is called I'll call this the loop C star, just to more easily refer to it. And so this one will act on the endomorphisms, and just to give some perspective, remember there was this Q in the quantum group. This will be the one which produces that extra Q parameter at the Grothendieck level, which gives you the quantum point of view with the quantum Q. So we could completely ignore this one, and we would get the same story, but without a quantum parameter. This one, I'm going to call it the scaling C star. And it's scaling because if you look at how it acts, it doesn't act on the phis, it acts on the x's by just scaling them. Okay, so this one is one which is really necessary and one I cannot completely do without for defining the T structure later on. So this one's actually more important. The critical thing about it, I'll say it now, but I'll repeat it later, is that it acts trivially on the phis and linearly on the fibers here. So again, it acts trivially on this guys, and it acts on the fiber-wise, it acts with weight 1. In other words, it acts by scaling. So this would be these are the two groups that are naturally acting, and I'll denote by G hat the product of these two guys, which will act everywhere. Which acts, well, I don't know by G tilde A, the product of these two guys, which act on these moduli spaces. So to finish, the object we're interested in, before I illustrate it in some examples, the objects we're interested in are the moduli space stacks, which is the quotient of these guys. I'll denote it by chi A, which is the quotient of these guys by these groups. Okay, and the categories we're interested in are the derived categories of coherent sheaves on these guys, which if you want to avoid talking about stacks, which is perfectly fine, you can think it's the same as the derived category of equivariant sheaves on these spaces. Okay, so in a summary, these are the categories we're interested in. And the next thing I should explain is how these categories have a monoidal structure. But before I do that, I guess I will maybe illustrate a little bit of what these spaces look like in a couple of examples as suggested, okay? So let's see. So a few examples here.
So, quick question. So that the notation MA upper SA is exactly the derived kernel of the bottom map SA, right?
Exactly, yeah.
Mm-hmm.
Yeah. So it's a derived moduli space of
And the group of G hats, which is acting on MA, and will be preserving all this M sub A and also the smaller one.
That's right. A priori they act here, but it's pretty clear that they will preserve this, and therefore, and in that commutative diagram, it'll commute with the maps. I just erased it, but it commutes with the maps.
I understand.
Naturally acts on the fiber product.
Okay, go ahead. Thank you.
Okay, so let's see, what kind of examples can we do? So the simplest example is when Q is just a point, okay, or even a bunch of points. But let's say just say a point, then let's see, then so let me make a little chart here. So we have MA, SA, we have MA, and we have big MA. And we can have here. So we can have just a dot. Okay. This is the simplest case. So in this case, MA will just be there's no arrows at all. So there's no X's, there's just the phis. So this would be and CA.
Positive, negative, positive, and a tiny negative.
And this will be what I denoted here, nilpotent elements inside of there. And then this doesn't do anything because there's no bundle here. It's a trivial bundle. So this is the same thing as NASA. There's no bundle here as well. Okay. So this case of a vertex, which is actually quite important, this corresponds to nilpotent matrices. And of course, there's the groups, but the groups are closed versions. Okay, and then the next simplest one is not actually one with the loop, self loop, but maybe this one. I'll do that one. Okay, but we can do the self loop one too. So in this case, so this is let's say dimension vector A, right? So here dimension vector A1, A2, let's say. Then what is this? So this would be here, it would be and CA direct sum and CA2, CA1 and CA2, direct sum. Actually, you know what? Let's do the 1-1 case. Because anyway, that which is an example. So this would be here, it would be C direct sum C for the two endomorphisms of these guys. Direct sum, let's write it like this, from C to C. Okay? From this one to that one. This one would be the ones corresponding to nilpotent. So it's a three-dimensional vector space. This one would correspond to just adding the condition is nilpotent. Nilpotent of dimension 1 is redundant. Sorry, it's not redundant. It's the opposite. It's just 0. So this was just 0, 0 direct sum CC. Okay. And then what this one is, and this is maybe an interesting case for people who have not worked with these derived objects. Maybe we don't need this group stuff right now. So what is going on here? It's the derived intersection of so here we're looking at the endomorphism here composed with, let's say this map is alpha, composed with alpha, it should be equal to alpha composed with this endomorphism. But these are both 0, so this is automatically satisfied, right? So as a classical space, this will just be the same thing as this, as a non-derived object. But as a derived one, if you were to write it, you would get the picture of this is one-dimensional, so they'll have CC mapping to basically you'll have this picture.
It's a 0 map.
Basically by the 0 maps, both of them. So so remember this is just a vector space over a point. So this is C, C, C. These are all vector spaces, and the maps that you write down, I guess I have to write down the diagram again. It's an dimension exercise. I'm just gonna write down what it is. So it's gonna be this derived intersection of where the maps are 0. So what you see is
sorry, but why are both maps 0? Isn't one of them the 0 section?
Yeah, but one of them is a 0. One of them, well, everything is over a point, right? So it's just a question of what happening over the fiber. One of the maps is literally 0. It's this gamma 0 I wrote.
Yeah.
Right? So
both maps are 0 maps.
yeah, both maps are 0. The other map is a commutator relation, right? But in this case, a commutator relation is the commutator of 0 with this map minus this map composed with that one. So the commutator relation is automatically 0.
Okay,
So both
thank you.
maps are 0.
Oh, no, the other one is not 0 map. It's supposed to be the V direct sum with W. That's the graph.
I can write it all out.
You have two copies of that.
Yeah, okay, let's write it all out. Let's work it all out carefully. So you have what did I write? You have
Because V and W are the same in this case.
okay, we can write it all out, but it comes down to what I wrote when you simplify it. Okay, so that's what you have. One of them is gamma 0, right?
That's identity to the first component.
It goes to so alpha goes to alpha 0, and the other one is this gamma of the section SA, but in this case it's a commutator, which is 0 as well. So this also goes to alpha,
Understand.
right?
Yes.
And well, it'll go to alpha the image, right?
The image of phi, that's
It's
0.
and it's 0. So it would give you the locus where this goes to 0, right? In this case, everything goes to 0. So when you do this fiber product here, what do you get? Well, what you're saying is so let me just simplify it. You have C mapping to C2 mapping to C, right?
Mhm.
As x goes to x0, x goes to x0. So as a non-derived thing, this is just C. But as a derived thing, it's like the intersection of the derived intersection of 0 inside of C with 0 itself. So what is a derived intersection? Well, I guess I can write it here as well, in terms of algebras. But this would be C of x mapping to C of xy. Not going to do all of that. It's you get one copy. So the non-derived thing is just one copy of C, obviously. But they also have a derived part corresponding to the fact that they don't intersect transversely, right? If this intersected transversely, then they would just be
Oh, I see.
and there would be no extra derived structure. But what's happening here that they don't, when they intersect like 0 with 0 inside of C. And what is the derived intersection here? Well, it's spec of C epsilon, where epsilon is now has degree -1. It's something in homological degree -1. So what goes here is isomorphic to spec C of x, which is the C epsilon, where x is just where x is a normal coordinate. It's the coordinate of the C, and this epsilon is epsilon squared of 0, and degree of epsilon is -1. It lives in homological degree -1. Okay. I'm not sure how much you want me to work out this example of why you get why the self-intersection of 0 with 0 inside of C is spec C of epsilon or epsilon squared. But here I guess I can work it out. I don't want this to turn into a lecture on.
No, just quick question. Is it correct to think about it as the total space of a complex with C and 0 map between them? By total space, I mean derived scheme.
I think it's
because that is the complex that you get as a convolution of what you are trying to take the fiber product of.
I mean, yeah, I'm not sure how to say. I mean,
Yeah,
it's
I mean,
this thing thought of as a G. This is a differential graded algebra with trivial differentials and degree of epsilon -1. So you have this C of x in degree 0 and -1.
Yep.
Okay. In terms of the cohomology of this guy, so this is a scheme. It has a structure sheaf which is given by this algebra. This algebra would normally, if it was classical, be supported in degree 0, but it's not classical now. It's supported in degree 0 and -1. In degree 0, it's C of x, and in degree -1 is 0 of x. And this is the generator here is epsilon, right? And epsilon squared is 0.
Yeah.
So it's this guy. And you see that this has to be like that because you want base change to hold here. So base change, if you push this forward here and you pull it back, and you were doing it in the derived category, then the push forward here, pull back in the derived category would give you not just a structure shift here, would give you a structure shift in degree 0 and minus 1. We can do this example, right? This is a standard resolution of the resolutions of this guy in there, right? So right, we call this I and J. Then how do you complete I lower star, J alpha star? So this, you push it forward and you resolve it here. So this is O of C. Resolve this, you have O of C, multiplication by X, and then you apply with J alpha star, and this gives you O of this guy, mapping by 0 of O of that guy. So you're getting two copies of this in degrees 0 and minus 1. So when you go up and here, this would just give you the structure sheaf here, goes to the structure sheaf here, which just gets pushed forward to a point. You just think of it as a vector space. So you can see that the dimension of whatever goes here should be one dimensional in degree 0, one dimensional in degree minus 1. And this is what it is in this case, if ignoring the C bracket X, right? So basically, the derived algebraic geometry stuff is such that it's a formalism which allows you to put the right fiber product here so that the base change works always. That's all that it is. And you can see that in such cases where the intersection is non-transverse, like this case, then you can't put a normal scheme here because this composed with that in the derived category is not just something supported in degree 0, of course. It's supported in many degrees. So this has to be supported, has to be a scheme whose structure sheaf is supported in many degrees. Okay? If you want me to talk more about this, I can definitely do it.
No. I think you explained too precisely.
So the moral of all this, you can work it out. It's a good example. Is that in this case, this guy here is exactly isomorphic to this space. Okay, namely the C bracket X, the spec C bracket X is this, and then there's a derived direction which is the epsilon. So you get sort of two copies of this guy in homological degree 0 and minus 1. Okay. All right. Well, I can work out more examples also later on with this sort of thing to see how it works out. But for the moment, I can just say it's a formal space, which is sort of has it's like a non-reduced scheme, right? There's the reduced part of it, and there's some extra non-reduced part of the scheme. Likewise here, you have it's completely analogous to that. You have the classical part, which is like the reduced part, which is the original scheme, just a naive intersection, the naive kernel. And you have some extra sort of non-reduced part. The only difference is that this is non-reduced, but the epsilon is a homological degree minus 1. Otherwise, it would be literally, if this was in homologically 0, this would literally be a non-reduced scheme. It's completely analogous. Okay. So let's see. I finished exactly at 3, is that right?
No, you can go all the time, yeah.
What's that?
You can go all the time a bit. I mean,
okay, so let me try to just get to a natural point and I'll stop.
Yeah.
Okay, at least get the good definition. So these spaces right here, these chi-A's have an actual convolution product, which is defined. Well, I'll quickly sketch it, but you can probably guess. So you take two let's say you take two vector spaces, two graded vector spaces. I don't know, V and V prime. I guess it's just I notation. Dimensions A and B respectively. And then I'm going to note by PAB inside of GAB the parabolic fixing, so GAB, this is GLN and so on. So this acts on the direct sum of these two. So parabolic fixing VA inside of VA plus VB. So remember GA was GLAI and GLA plus B acts on the direct sum. And we're looking at the parabolic fixing them, fixing this guy inside of there. And there's so that's the group, analogous groups we need. And then there's analogous spaces, which you have big fat NAB, which is, you can probably guess, it's pairs P of X. I guess I can't write that. So you have MAB, which is P and X, such that P of I belongs to the corresponding the algebra of PAB. So it's the algebra of these guys. So they're endomorphisms of this, which fix VA rather than automorphisms. And the XE, so the X's are say direct sum again over the E's of Palm of the direct sum VI prime into it's analogous to this, say primes into okay. Hopefully that fits. It doesn't. There we go.
Good.
So it's yeah, it maps from the head for each tail, for each edge. It maps from the tail to the head of the corresponding V for the sum. Okay, so and obviously in here you have MAB, which asks, I'm not going to rewrite it, asks for the fees to be nilpotent. And inside of here, you also have MAB, SAB, which again is the same thing, asking for the fees and the x's to commute. You write down the formal, the same formal spaces. And this maps over NAB, which is the analogous space where you forget the x's. So this would be just a bunch of so originally NA is a product of nilpotent cones, and this is whatever you want to call them, partial nilpotent cones. Okay, so there's the analogous spaces. It's completely the same, except that you're asking for some sort of parabolic condition on the phi's and on the x's, and then you can consider the same analogous stack, which is the quotient of this guy by this group G, sorry, PAB over there, the parabolic. And there's also, just to be precise, there's also a P hat where you multiply by the T. The T just flows along everywhere. So we could ignore it for now. But let me just add it in because this is precisely the space. And then we're almost done. So then you have this guy, chi B is a stack, and you have a map, you have two maps. One of them is to chi A, one of them is to chi B, by just remembering the action of phi on VA on VA or VB and so on. And then you also have a map to chi A plus. Okay. And we'll denote these maps by AB and MAB. And you can use these to define the convolution. So you define, so say you have FA coherent sheaf on this stack, and similarly for FB. So again, what that means is it's a when I say coherent sheaf, I mean a complex of coherent sheaves on this derived stack, or equivalently on GA covariant sheaves on these derived schemes, and you have a pair of them, and you define their product as follows. You pull them back, take exterior product, you pull them back, and you push them forward. And everything is derived, of course. All the functors, everything is derived. Even the spaces. That's the point. So that's the convolution product. And
is it well defined? Do you need some properness somewhere, or you don't?
Right. So there is something to check here. There's something to check here, namely that it sends coherent sheaves to coherent sheaves. That's right. So for example, you need this thing to preserve coherent sheaves when you pull back, and that's not completely clear because things are derived. So for example, if you have C mapping, spec of C mapping to spec of C epsilon mod epsilon squared, like we saw might happen, then the pullback here does not preserve coherent sheaves, right? The derived pullback, because you get an infinite complex. So you have to be a little careful that this thing preserves pullback, preserves coherent sheaves, and also here push forward is to point out in some sense this has to be proper, and it is proper. Okay, it's proper basically because if you forget about if you just at this level, it's something you're probably more familiar with. The fibers would be something like GL A plus B mod P A plus B. The fibers will be the portion of GL A plus B mod P A plus B. So that's a proper thing. And then you have to be a little careful about the other fibers. But it's a formal argument. So it's not deep at all. It's just going through the definition and checking that when you write things out, that the maps are of the right type. It's an elementary check, but it's not true. It's not a priori. There is something to check, but it's minor. That's right.
Excuse me, for the definition of the boldface MAB, so the component XE is just looks to be any element in this A plus B.
Sorry?
So
So here, A is a tuple, right? And so is B?
Yeah. Well, on the top of the board, for the component XE, the corresponding to the arrow E.
Yeah.
Can't see that the direct sum from V prime from the right hand side is also the second receiving side is just the V prime or just the V.
Oh, here. Sorry, this.
Oh, okay. So basically, that you don't have any restrictions on the XE, but only have the restrictions on the phi parts.
Oh,
so
sorry. You're right. You're right. I forgot to put it. Let me see the right way.
Yeah, so I thought that the XE should give a sub-representation.
Yeah.
VA should give a sub-representation.
Yeah. So you want this
it's the same diagram which defines the product in the whole algebra.
Yeah, you want to fix the VA. Yes.
That's right. It's the same product. It's the same diagram.
Yeah.
So yeah, you want basically you want phi and x to preserve VA.
Yes.
Yeah.
So pretty much the same thing as what Lustig did. Just
yeah. No, there's nothing. There's nothing. There's nothing.
No. But associativity, which you probably now explain, it's not exactly. Lustig deals with, I believe, with constructible sheaves. No,
That's right. But the setting up of before you get to the shift level,
yeah, it's
the
all
stack
same.
level is pretty much the same.
It's whole package.
Yeah, so
Mhm.
for some
Whole
to
package.
work out nicely, so basically you need things to be derived so that you formally have diagrams, these fiber product diagrams, which you know have the right properties, and then it's just sort of a lot of it is just chasing diagrams and checking that things work out. And just to be precise, also for the later notation, there's some shifts here, which I'll write down just to have them written down, but they're not really crucial. But for those that like details, there's some shifts here. So I'll explain what the shifts are. So first, these are just numbers, and I'll write them down just to have them. This is really secondary, but I don't want to write down the wrong formula. And then I'll explain what their significance are. Yeah, so that's just some numbers. I'll explain in a second. This notation means this is the cohomological shifts. The usual notation for shifting down by one. Shift by bracket one means shifting down by one. And this is the equivariant shift. This notation for equivariant shift for loop C star. So parentheses one means equivariantly shifting by one for the if you remember there were two C stars for the loop one. Again, you can forget completely about the loop C star, which means that you're going to forget the quantum parameter, and this is irrelevant. This just makes everything work out a little nicely and match up nicely with the quantum group picture. But it's just to make things nicer. This is a little more important because again, you could remove this and it would be a well-defined product for elementary reasons. But this shift is necessary to make the T structure work out properly. So these are in some sense dressing up, but this one's a little bit more important than this one. Okay, but anyway, that's the definition. So it's the obvious thing up to some silly shifts. And oh yeah, so what these numbers are again, yeah, they're this one, as I said, is important for the T structure, so that things stay in the T structure. And this one is really just to make things work nicely with respect to the usual.
And when you say the loop shift, your torus is two-dimensional. So
the other one
acting on the nilpotent part by T squared, that's the standard K-theoretical approach to the loop. The grading from the nilpotent variety by the T squared, that's T1 acting. And you also have the second copy of the C star.
The other one, which then the shift for the other one, I'll denote like this. It doesn't show up in the definition here.
Yeah, and here you said for the loop C star. So which one of those is the loop C star?
The loop one is the one that acts by T1 squared.
T1 squared is the loop. Okay.
Yeah, the loop one is the one that acts on the loop.
Okay.
It acts on the endomorphism, which are the loops.
And the second one is a scaling.
The second one just acts on the scaling on the axis. Yeah.
Okay, thanks.
Yeah. So the way I remember it is it's actually called a loop for more than one reason, but I'm calling it the loop here because it's acting on the endomorphisms, which you should think of as the loops on the quiver. Whereas the other one doesn't, just scales on the other factor, on the x's. Okay, so some minor remarks. Maybe I can just jump over them. It's not so important. And maybe I'll finish with this, and I'll start with the T structure tomorrow. This is sort of put things a little bit in perspective. What's happening here, and why we're considering this particular diagram with which is not the pre-projective one. So let me try and explain it a little bit. So the idea, sort of an aside, the idea is that it's the following one. There's something called, dimensional reduction, which has various meanings, and I'm sure you're more familiar than me with this concept in some context, at least. But let me be precise what I mean by in this case. So this goes back to work of well, Isaac and some other people, and here on. And the statement here is the following one. I'm going to use a notation earlier. So let's suppose you have, from using the notation earlier, suppose you have a map of vector spaces V to, in this case, the same thing, V. Okay. Then the claim is that this dimension reduction says that if you look at it's C star equivariant coherent sheaves on V, where the C star is scaling, just like our scaling, then this on VS, sorry, the kernel, the derived kernel of this, then this is equivalent to graded matrix factorizations on V direct sum V dual with some potential.
This part of the blackboard is not visible.
Right, I forgot. Is this good over here? So this
Yeah.
is equivalent to graded matrix factorization on the direct sum of these two guys with some potential.
Yeah, I think at the level of cohomology, it's in our paper with Maximov 2010.
Right, yeah, so the cohomology.
Yeah, I mean, it's exactly the same. We didn't use this terminology, but it's the same, yeah.
Yeah, that's right. And so if you look at if you apply this in a particular situation, erase this thing, definition. So again, this is not crucial, but it's just to put things in context. Then you get the following thing. On the one hand, so we have our chi-x, and let me denote the, I guess we have a name for it. So we have chi-a and we have y-a, the big space without nilpotency condition. Right, so this is like the MASA, this would be like big fat MASA, okay? Okay, so you have the following picture. You have coherent sheaves on the stack YA, and this is equivalent if you apply this result to matrix factorization on this is over the x here is the endomorphisms, and the vector bundle is the x's. So you have x together with the dual of x, which is the arrows going in the opposite direction. So here you're going to have the space of representations of the triple quiver with some potential. Okay, so the dimensional reduction can go this way to get to R spaces. R spaces are not exactly these guys or that guy, but that's you can think of it as sitting in here. Okay, for the moment. On the other hand, you can reduce in a different direction, namely here reducing by taking one set of the arrows and kind of getting rid of them. But you can also try to get rid of the loop. And if you do that and get rid of the loop, you end up with an equivalent in the other direction with the drive category coherent sheaves on the representation category of the pre-projective algebra. This is moduli of reps on Q bar, on the quiver Q bar, if you remember with arrows in both directions, together with the pre-projective condition. Okay, so that's it. So what's happening is, in principle, you want to work here, okay? And what we're saying is, well, you could work here by dimensional induction. You can also work here, but on the other hand, you could also work here. All right. And the reason it's advantageous to work here is because then we can consider this this very natural subcategory consisting of nilpotent matrices. And this is where the T structures will live. And I think as subcategories, I think you can identify this here with a certain subcategory of this guy, consisting of coherent sheaves with what's called nilpotent support, in the sense of nilpotent support, in the sense of Rankin and Gates-Curry. Okay, so anyway, that's roughly the picture. That's not how I arrived at this just by following the picture, but that's how I think of filling it in. You want to work here, but it's actually a little simpler to work here because it's much simpler to define the subcategory as just sheaves supported on the nilpotent cone rather than as sheaves with this nilpotency condition defined by Rankin and Gertz-Gray, which is much more complicated to work with. All right, so everything I'm saying in some sense can be interpreted as just doing it here, but it's much harder to do the whole argument here than it is here. Also, this was influenced by some other ideas as well. But that's the picture.
Yeah.
So this explains sort of the relation to the triple quiver and also the relation to the what's usually studied more commonly, the pre-projective moduli space.
Yeah, so for me this dimensional reduction is like going from three-dimensional Calabi-Yau in your case to two-dimensional Calabi-Yau. So your loops are just this extra, if you like, line or whatever. But this subcategory coherent shifts on XA, since you identify it by horizontal arrow with something three-dimensional, what it corresponds to a kind of geometry by this analogy, because representations of PQ, it's like, like Higgs bundles. This analogy with geometry is pretty clear. So then the top line is three-dimensional at the level of matrix factorization. I think Tudor Podorario, he kind of makes it consistent working with this graded matrix. All right, but this so it's equivalent to some coherent sheaves on a big stack, no nilpotency. Inside, you have this substack coherent sheaves on XA, but in terms of this whatever three-dimensional Calabi-Yau category, what is it?
What is a sub guy? Yeah, I'm not sure.
Yeah.
Yeah.
If like, by analogy, like imagine that you have, I don't know, let's forget about two-dimensional Calabi-Yau, kind of like P2, and then you go to the total space of the canonical bundle. It's like three Calabi-Yau, for which you consider something less MF graded. It's some category of sheaves which lives on three-dimensional Calabi-Yau.
Yeah, I'm not sure. I'm guessing that maybe at this level, I mean, directly or yeah, I don't know. Like if you want, you could try to generalize this to somehow beyond just the category of.
Well, you did, because what you did with Williams, it's it's kind of you define the T structure, yeah. So that's an I'm keeping in mind that story as well.
Yeah. Um, yeah, I'm not sure what I can really say that makes coherent sense. I
Yeah.
can't speak very much about
Maybe constructible
what
set.
sense does this category have. Much more, in that context. I'm not sure.
Yeah. But anyway, it's it's extremely interesting. Yeah. Okay. Maybe some other any questions to Sabin for his today's lecture?
Yes.
Okay.
So in your definition of this modulus space, the MSA sub A,
Yeah.
you defined, and it seems to me that if I give one single is just take the original quiver instead of looking at the representation of that original quiver Q over the field, but I'll look at the original quiver taking the representations of the nilpotents at each vertex attaching nilpotent representations of a Jordan quiver, which is so it's the same thing. Of course, this time the Jordan quiver, this representation category is not semi-simple. So one way is to take the original quiver Q representation and then take a nilpotent nilpotent atomorphism. That's the Q, the MA S super SA.
Yeah, that's right.
So another one is to just simply look at the representations of the quiver over a different category, and the category is the representation category of the polynomial ring, nilpotent representations of polynomial ring.
Yeah, I don't quite understand what the second one is.
So that means at each vertex, instead of attaching a vector space, attach a module, finite dimensional module for the polynomial ring.
For the polynomial ring.
Yeah. With the X acting as nilpotent.
You want to put more than one you want to put many loops, you mean?
Well, it's just one. In your case, it's only one single loop. Yeah. That's why there's only one single variable polynomial.
It's a module over C bracket X if you want.
Yes. Then nilpotent representation. That's a full abelian subcategory.
So you want to consider, instead of a module over C bracket X, you want to consider each vertex a module over
That's right. That's right. So I can.
Yeah, I mean, that sounds like you want to put more arrows here and ask that they commute.
No, just one single arrow. So in this case, with one single variable.
Yeah, that's what
so that is basically looking at the things over the nilpotent con, and your NA, those are exactly just for each vertex you NA.
Without the condition that they commute. Yeah. That's right.
So the whole picture here, as example, and everything seems to be over with one single vertex, no arrows.
Yeah, if you have one single vertex, then
so that will goes back to the
equal to that, right?
Shifts over the nilpotent con.
Yeah, so if you have one single vertex,
right.
To that, and if you have one single vertex with an arrow,
but that has to be nilpotent. So this is a classical D theory.
Right. So for this one, you're gonna have the phi plus the x. So you're gonna have two endomorphisms.
Well, this time there is no arrow, so there is no x.
Okay, so you want no arrows.
Yeah, just the quiver Q is just one single point.
Okay. And so in my case, this is just not very interesting. This is just NA.
That's exactly a nilpotent variety in D corresponding to the D algebra.
That's right.
So is this something which is known or in your construction?
Yeah, I think it's funny. It hasn't. I mean, in this case, you're just looking at nilpotent cones, and you're doing
Yes,
this.
that's a
It kind of is known, but it's not actually written explicitly in so
well,
much.
In Ginsburg's book, he did a lot of work on this K-theoretical on the nilpotent varieties, equivalent shifts on the nilpotent varieties.
Yeah, I think it's been
And
studied as
with a
well. So,
loop, I mean, one of the copy of the C star is the loop action. That's the T square acting.
yeah, exactly. Yeah.
Mhm. So I was wondering if you are aware of this special case, which is something looks like what in Ginsburg's book.
I don't know. I mean, I don't know. I don't know all the literature so thoroughly. I think it's understood. Yeah, in the literature, it's understood really well.
Okay.
The case of just one vertex.
Yeah, in particular, I believe he used the K-theory construction, but heck algebras, lots of things in the book.
Yeah, I don't know the book per se,
Uh,
what's in that, but yeah, I
Okay.
think in this case it's sort of yeah, I hate to say understood by experts, but
Okay.
just an
Yeah.
excuse for not being able to give you a precise citation for the case for this case.
Mhm. Okay, well, thank you.
Yeah.
More questions? Well, if there are no questions, so thanks Sabin again, and we'll see him tomorrow at the same time. Yeah, thank you
Okay.
very much.
Thank you.
Bye.
Tomorrow.